Homework last night was page 63, number 2 to 16. Any issues? Yep, Haley? 14? Oh, I love that question. I'm glad you asked that one. I remember that one now. Yep. Okay, 13, 16. Yep. 2. Two, 8, 13, 14, 16. Yep. 3 or 4. Okay, quite a few of them here. Okay, so let's get at this here. Number 2, what determines how long it will take an object to reach the ground when released from an initial velocity of 0? Give me one thing. Gravity. Okay, if you're on the moon, it takes longer for it to reach the floor than it does if you're on Earth. Gravity is about 1/6 on the moon what it is on Earth, about negative 1.6 meters per second squared. Okay, gravity is one thing. What's the other thing? What? No, actually, the weight of the object doesn't matter. The weight, mass of the object, everything falls at 9.81 meters per second squared. If you're on Earth, that is. Everything falls at that rate. In the absence of any other forces, right? Correct? Well, yeah, we'll always ignore air resistance. So the surface area would affect air resistance, you're right. But we'll pretend that air resistance doesn't exist. Yep. Okay, but you said gravity, right? So same thing, acceleration due to gravity. We're missing one pretty obvious one here, again. Yeah, Jacob? Well, the initial velocity is 0, right? So what affects it if it's always released with an initial velocity of 0? Displacement. How high is drop from? You drop something from the top of your desk versus the top of a 55-story building in downtown Calgary, it's going to take longer to hit the ground, right? If you drop it from the 55-story building. 3. A student drops a bran muffin from the roof of the school. From what height is the bread muffin drop if it hits the ground 3.838 seconds later? Here's our time, 3.838 seconds. Is that all I have? Okay, it's time to get to work. You reading between the lines masters here. Seth? We have VI as what? Good. Starts at rest, right? Yeah. Good. Acceleration is negative 9.81. What are we looking for? From what height is it dropped? What's the variable we're looking for here? Displacement. Displacement is technically not the height. It's technically how far the object has fallen, right? But if we get a negative 55, then we know that the height of the building was positive 55. So let's get that now. Let's say D is equal to VIT plus 1/2 AT squared. That's not the only way to solve this, but I think it is the most direct way to solve this. Cross that off because VI is 0. 1/2 of negative 9.81 times T squared, 3.838 squared. That's going to give me, I don't know, about 80, 70 something, 72.3, negative 72.3 meters, which means the height of the building would be 72.3 meters, right? How many people got that? Did it occur to you when you got that that's a really high school? Like, that's a big school, 72 meters high. Our school might be, well, on this floor, it's probably about 4 meters high. Okay, and when we have over there in the social and English wing where we have 2 stories, it's probably more like 10 meters high. Okay, 72 meters is a big, big building. Okay, it's a good thing it's only a muffin he's dropping instead of a rock or something like that. 4, during a babysitting assignment, a babysitter is constantly picking up toys dropped from the infant's high chair. You know why the baby drops them? Because the babysitter keeps picking them up. Stop picking them up. Maybe the baby will stop dropping them, right? The baby is smart enough to condition the babysitter into picking up the toys. Look, if I drop this, the babysitter will pick it up. Ha-ha. The toys drop from rest and hit the floor 0.56 seconds later. From what height are they being dropped? Let's hope that this one's not 72.3 meters. Let's hope it's a little bit smaller than that. Here's our time. Once again, we're looking for displacement in this question. VI, same things, right? VI is 0, and A is neg 9.81. I think we're going to do the exact same thing here, aren't we? D is equal to VIT, which disappears because VI is 0, plus 1/2 AT squared. So it's 1/2 of neg 9.81 times 0.56 squared. I'm going to say that's somewhere around 1.1 meters-ish. Do you have that? 1.54 meters? Okay. We're going to round that to 2 digits, actually, because of that. Okay, 1.5 meters. That's actually negative, right? The height would be 1.5 meters. The displacement would be negative 1.5. Listen, if you get a question on a test that asks you for the initial height, and you actually solve for the displacement and make it negative, I'm not going to take a mark off for that, even though technically the height is positive, right? Yep. Yep. No. Leading zeros are not significant. If it was 0.560, the final zero would be significant. Okay, so leading 0 in the beginning isn't, the 0 in the end is. Or zeros in the middle are as well. Yep. No, when you throw something, the initial velocity isn't 0. Okay, we're not talking about before you moved your hand. Okay, the initial velocity would correspond to the moment it left your hand. And when it leaves your hand, it's moving. So VI in that case would be something other than 0. You'd have to be given the value there, right? No, VF wouldn't be 0. It hits the ground, right? But was it Haley that we did the little hole puncher demonstration on? It's VF wouldn't be 0, right? If we drop that hole puncher on Haley, which of course we're not going to do, because it's going to hurt, right? But why is it going to hurt? It's going to hurt because it's moving when it hits, not after it hits. Okay, all bets are off then. But when it hits, it's moving. So VI wouldn't be 0 in that case, nor would VF be 0 in that case. We'd have to be given some values though. All right, next question was, what do we got? 2, 3, 4, 8. If the acceleration due to gravity on Jupiter is 24.8, that's 2.5 times what it is. Imagine trying to walk around on Jupiter. If you weigh, let's say, 150 pounds on Earth, okay, you would feel like you weigh about 375 pounds on Jupiter. Okay, that would be difficult. Okay, that would be difficult to walk around. Determine the time it takes for a tennis ball to fall 1.75 meters from rest. So this is A. Okay, we'll make it negative 24.8 meters per second squared because it does cause things to speed up as they fall. The displacement would be negative 1.75 meters. And it says from rest, so VI would be 0. We're looking for T. How long will it take? A, D, VI, and T. What do you want to try here? Maybe this one? Yeah, Louis, go ahead. Good, that's exactly the one that I was going to suggest there. But we're solving for T. A little bit harder to solve for T, though, isn't it, to solve for V? VI is 0, so that makes it quite a bit easier. We got to take the 1/2 A over by dividing. D over 1/2 A. What's the other way, by the way, to get the 1/2 over? Instead of dividing by a half, we could have, Stephanie, multiply by 2. So either way works just fine. If you multiply by 2, you'll get the same answer as I get here. That's equal to T squared. So T will be equal to, now we got to get rid of the square by square rooting. Square root of D over 1/2 A, or alternatively, the square root of 2 times D over A. Both the same answer. Neg 1.75 divided by 1/2 of neg 9.81. And what do we get for the answer then when we do that? My guess is it's going to be a pretty quick time interval here. It's only falling 1.75 meters, and it's falling at 2.5 times the rate that it would on Earth. What's our time there, Louis? Okay, that seems reasonable to me. We know it's going to be a really, really small time, right? We're actually going to round it to 3 digits though, Lewis. 1, 2, 3, 1, 2, 3. What is it? 0.3. Okay, 0.370. Okay. 0.3755. So we're going to say 0.376 then. Okay, so if you happen to round it to the wrong number of digits here, don't lose any sleep over that right now. Okay, I won't take off marks for significant figures until after your first unit test. Okay, once we've had a chance to really work on that. Good. Next question. Holy cow, there's lots of them here. 13, 14, and 16. 13 says, if a diver starts from rest, determine the amount of time he takes to reach the water's surface from the 10-meter platform. 10-meter platform, that doesn't sound like very far, hey? It's far. Okay, it's far. We did an experiment one day, this physics/biology project one day. We went to Lindsay Park, or Talisman Center now it's called, I guess. It was on the physics and biology of diving. So we got the diving pool all to ourselves. And, you know, they have the bouncy diving board. And then they have the 5-meter, I think it's the 5-meter concrete platform. And then they have the 10-meter concrete platform. I can't remember if there's one above that. I think. Okay, yeah. I mean, Talisman Center is, you know, like for training Olympians, right? So like it's the real deal there. I stood on the first concrete platform to jump off, and I think it was 5 meters. It's only 15 feet, right? 5 meters. But the pool is so crystal clear and it's so deep that it looks like you're about 50 feet or 100 feet up as you're looking down. I'm standing up there and thinking, this is 15 feet up. I should be able to jump off of this. But I was terrified jumping off this 5-meter platform. We had a couple students actually jump off the big one, the highest one, which terrified me to even watch them jump off of that one. You know, when they, by the way, when you have these diving boards or these diving platforms, you know, 10 or 15 meters up above the water, they actually have a bubbling system to bubble up through the water. Do you know why they do that? Nope. The water is bubbling the whole time as you're jumping off of, not like the 5-meter doesn't matter, right? But if you're on something that's really, really high, like 30, 40, 50 feet up, they want the water to be bubbling as you're jumping off. How come? Yeah, there's a lot of, you guys learned this in Science 10, right? There's a lot of surface tension in water. Okay? If you do a belly flop in water, it hurts, right? From a meter. If you do a belly flop from 10 or 15 meters, it could kill you. Literally, it could break your spine, literally. So they bubble the water, and that breaks the surface tension, so that if you do happen to land wrong, it might not be comfortable, but you don't get that, basically that force of landing on concrete, which is almost what it would feel like if you did the belly flop. So you ever see them diving in the Olympics, you'll always see the pool bubbling below, just in case they land wrong, okay, so they don't kill themselves. Okay, question number 3, we've got a displacement here of negative 10 meters. VI is 0, starts from rest, right? We're looking for time here, and of course we've got the acceleration is negative 9.81. Pretty much the same question as the last one, right? Right, rearrange d is equal to VIT plus 1/2 AT squared to solve for time. In fact, because we're running out of time, I'm actually not going to do this question. Okay, we rearrange it the exact same way as we did the last question. We solve for time the exact same way, just happens to be a different number, that's all. Okay, if you have, try that again this weekend. If you struggle with that, let me know on Monday, and I will go over it for you. I'll help you with it. But since we just did one identical to it, we'll save ourselves a little bit of time today. 4, we will, oh. We just did that one, right? What did I copy over 4 here? Is that, oh, that's 14, okay. Okay, boy, am I ever confused right now. I thought we just did one like it, but I didn't think we did the exact question. Boy, oh boy. That's what happens when you get 42 years old, guys. You start remembering one moment to the next. Okay, 14, like this one. A person in an apartment building is 5 meters above a person walking below. She plans to drop some keys to him. He is currently walking toward a point below her at 2.75 meters per second. How far is he if he catches the ground or catches the keys 1.25 meters above the ground? That's a tough question. That is a tough question. We got two things going on here. There's the fall, and then there's the guy walking over here. Let's write down givens for both. For the fall, the displacement is what? Let's finish this question, guys. Okay, we won't finish the next one, but we'll finish this one and leave it there. The displacement is what for the fall?
Emma Thorne to the front
No, it's not 5.
Jacob Brown to the front office, please. And Jared.
3.75. The keys don't have to fall 5 meters. The keys have to fall 3.75 meters, right? Does that make sense? Because he catches them 1.25 meters above the ground. VI there would be 0 meters per second. A would be neg 9.81 meters per second squared. This guy has to walk 1.25 meters horizontally. His acceleration is 0 because he's going at a constant velocity of 2.75. No, that's wrong. But his velocity is 2.75 meters per second. Okay, we want to find out how far away is he. In other words, how far does this guy have to walk? Well, let's get the time up here. Okay, let's get the time up here. Let's say for stage 1, the fall of the keys, d is equal to VIT plus 1/2 AT squared. This disappears. Let's get t the same as we did in 13 and the same as we did in that other question. Let's get the time. That's how long it takes the keys to fall. How long does this guy have to walk at 2.75 meters per second? Whatever the time was of the keys falling. So let's take this equation, since he's walking at a constant velocity, rearrange it. Rearrange it to solve for t. For d, I mean. D is equal to v times t. And multiply 2.75 by however long the keys fell. That will tell us how far that guy has actually walked. Does that make sense? Anybody do it that way? All right, good, excellent. That's a hard question. All right, let me know if you have any questions on any of the rest of them on Monday, guys, and then we'll pick it up with V versus T graphs on Monday as well. Have a good weekend, everyone, and we'll see you on Monday.